Okay, welcome to day 2 of Unit 7. It's more vectors, and we're going to do something called dot product. I'm going to try to do it where when I use a stylus, I don't make it click so much. I'll try my best. So today, the first page is going to be a review of what we did on day 1. Feel free to skip this part of the video if you want. Again, we're dealing with things called vectors. A vector is a magnitude and a direction. And again, we use this notation. This letter with this little half arrow on top of it. A vector is made up of two components, an x component and a y component. And we use, as an example, 5, 3 with these pointy brackets. These are not parentheses. I use these pointy brackets to represent that it is a vector. So when we write things in component form as 5, 3, that means I start at the origin 0, 0, and I end at the point 5, 3, and that's where the arrowhead is at. A vector, scroll up, has two things we're talking about. Magnitude and direction. So the first thing we have to look at is magnitude, and I use basically the Pythagorean theorem or the distance formula. That is the first formula I use. And the second thing I look at is direction or the angle theta, and I use inverse tangent for that. But let's be careful. Let's pay attention to the quadrant of the vector. 5, 3 is in quadrant 1, so when I do inverse tangent, I better get a quadrant 1 angle. As an example, this is exactly the same one we did last class. We have 6, 5, which is in quadrant 1, and I want to do its magnitude. So I'm going to do the square root of 6 squared, 5 squared, to get the square root of 61, which is going to be, let's see, clear this out, square root of 61, and I get 7.81 about. And then I want to do the direction theta, and I'm going to do inverse tangent of the y over the x, and I'm going to put this in the calculator. Make sure you are in degree mode. In the calculator, so when you go to the calculator, the mode key, make sure that you're in degree mode. I'm going to do inverse tangent of 5 divided by 6, and I put this in the calculator, I got 39.8 degrees. And 39.8 degrees is in Q1, and my vector 6, 5 is in Q1, so they do match. So the idea is that if you know the components, if you know the x and y component, you can find your magnitude and direction. All this is reviewed from day 1. In fact, that's the exact example I used from day 1. Okay, now for the new content, page 2. we're going to work with things called unit vectors. A unit vector is any vector that has a magnitude of 1. So when I talk about a unit vector, its length is equal to 1. There are two very special unit vectors. They are the horizontal vector and the vertical unit vector. We use the letters I and J. So I with a little vector hat on it is the vector 1, 0, which is right here. And J is the unit vector that is in the vertical direction, or 0, 1. So there's two ways to write unit vectors. One is in component form, 6, 5, or another way is to write it as 6i plus 5j, where I represents the x component and j represents the y component. Okay, let's talk about how we can prove this. Pick green. Okay, well, let's see. 6i plus 5j is equal to 6 times 1, 0 plus 5 times 0, 1, which is equal to 6, 0 plus 0, 5, which is equal to 6, 5. And it works out. So the idea is that there's two ways to write it. Zoom this up a little bit. Oops. I can write a vector as component form, which is right here, with your pointy brackets and Vx comma Vy, or I could write it in this other form, which is right here, with the i's and j's, and sometimes I call this linear combination form. Okay, they represent the same thing, as I said. These two things are the same. 6, 5 is the same thing as 6i plus 5j. Okay. Scroll down. Okay, now we're going to talk about making unit vectors based off an original vector. So, a unit vector is the same direction as the given vector. Change it to as magnitude of 1. It will be a vector in the same direction as the given vector, but its length would be shrunk or stretched to 1, depending on what needs to be done. So what I need to know the original vector, Vx, Vy, and I need to know its magnitude. Okay, and all I'm going to do is divide the original vector by its magnitude. As an example, vector 6, 5, which we've done a lot today. We've already said that the magnitude is the square root of 61, which is about 7.81. So when I want to do this vector, it's going to be 6 divided by the square root of 61, comma, 5 divided by the square root of 61. And I put this into my calculator. Calculator. 6 divided by the square root of 61. And 5 divided by the square root of 61. And those are my two results. And I get so vector u is a unit vector based on vector v, 6, 5, and the new components are 0.77, 0.64. That means it is the same direction as the original vector, but has length 1. Let me show what I mean. Scroll this up. So there's my vector, 0.77, 0.64, and I'm going to draw that. 0.77, 0.64 is right around here. So this red vector is vector u, and its components is 0.77, 0.64. And it is the same direction as vector v, but magnitude equal to 1. Okay, that is page 2. So what we've done so far is I've given you components, Vx and Vy, you found magnitude and direction. How about the other way around? What if I have the magnitude and direction, and I want to find its components? Well, if we look at our picture by trigonometry, cosine theta is equal to adjacent over hypotenuse, or from this picture, the x component over the vector. And if I do sine of theta, sine is opposite over hypotenuse, which is the y component over the vector. Well, if I take those ideas and I rewrite them, I get v sub x equals v times cosine of theta, and v sub y is equal to v, the vector, times sine of theta. It's all calculator work. It's not that hard. Make sure your calculator is in degree mode. That's what we're working on today. So let's try an example. We're using these two equations. So I'm using those two equations above, and I'm going to draw my vector of 300 at 120 degrees, which is maybe right here. 300 newtons here, about 120 degrees. I want to get the x and y component. Well, v sub x is equal to 300 times cosine of 120, and v sub y is 300 times sine of 120. And I'm going to put them in the calculator. And where are we at? Make sure you're in degree mode. Degree mode. 300 cosine of 120. 300 sine of 120. And those are my x and y components. So my result is negative 150, comma 259.8. You want to draw this on here? Negative 150 and 259.8. That's what I mean by the x and y component. Okay, let's go to another example. Now, in this class, when we talk about compass direction, okay, (0 degrees is due east. 90 degrees is north, and so on and so forth. Okay, these are important. So for my next example, if I have a 250 miles per hour at southwest, well, southwest is between south and west, right in the middle. Is my 250 miles per hour, and it would be between south and west, or 225 degrees. If I notice, 225 degrees is in quadrant 3, and let's do my x and y component. Well, the x is 250 sine 225. The y is 250 sine of 225. And again, I can go to my calculator. 250 cosine 225. 250 sine 225. Oh, well, I should get the same 225 degrees, like a 45-degree angle. And I get my result as negative 176.8, negative 176.8. If I do this out, negative 176.8 and negative 176.8. And if you notice, my vector is two negative x and y's. That is quadrant 3. So let's talk about our summary. Here's my big picture I have. I have an x component, I have a y component, I have my vector, I have my angle, and here are my big 4 equations. The first two I use when I know my components. When I know my components, x and y, I can find my magnitude and direction. And the second one is when I know my vector or my magnitude and my direction, and I want to find its components. These are the big 4 equations. You should have them handy with you at all times to figure out what we're doing. Okay, the next part of this lesson, we'll be doing something called the dot product. The dot product is not a true multiplication of two vectors. It is something else. It gives you a very special result. Yes, we are just multiplying the components, but we're adding them together. Our final result is just some number. It is a scalar. It is not a vector. So if I do vector v dot vector w, I'm just multiplying the x components of v and w plus multiplying the y components. As an example, vector v is 4, 3, vector w is negative 2, 1, and I would do 4 times negative 2 plus 3 times 1. I get negative 8 plus 3, and at the end I have v dot w is equal to negative 5. Okay, it is just a scalar. It is not a new vector. And we'll talk about how we use it in a minute. Another example, 4, 1, dot negative 2, 8. So 4 times negative 2 plus 1 times 8. I get negative 8 plus 8. And I have v dot w is equal to 0. Seems like a special result to me. Let's look at why a dot product of 0 is special. Okay, I'm going to actually graph these two vectors. It's going to be harder for me because I can't really use a straight edge, but here's 4, 1. Here's vector v, which is at 4, 1. And vector w is at negative 2, 8. Here's vector w, negative 2, 8. And if I notice, when I look at the picture, these vectors are perpendicular. So when your dot product is equal to 0, you're going to get two vectors that are perpendicular. Okay, it's a very special relationship. So why would I use dot product? Well, I'm going to use dot product to help figure out the angle between two vectors. So I'm just trying to figure out, when I use the dot product, I'm going to use this formula here to figure out the angle between these vectors. So I'm going to rewrite it. Theta is equal to inverse cosine of the dot product divided by multiplying the magnitudes. Okay? Again, this is all calculator work, all in your calculator. Make sure you're in degree mode. Okay, let's go through an example. I'll do the one example full out here. I'll let you work on the other ones by yourself, and I'll put the answers up. Okay, so here are my two vectors. Vector v, vector w. I want to figure out the angle in between them. So I have to do the magnitude of v. I get 4 squared plus 3 squared, square root of. I get 5. Vector w, magnitude. when you do magnitude, you don't have to ever type in the negative numbers because anything squared is positive. So I'm just going to do 2 squared plus 1 squared square root of, and I get the square root of 5. My dot product, v dot w, which is the one I did before. So in our case, it would be 4 times negative 2, which is negative 8, plus 3 times 1, which is 3, and my dot product is negative 5. So now I want to be able to do theta equals cosine inverse of the dot product, negative 5, over the magnitudes, 5 times the square root of 5. Now, when you put this in your calculator, you have to do it one or two ways. One way to do it is to use this very special fraction key that we talked before. So I'm going to do second inverse cosine, second inverse cosine, and this very special fraction key is alpha, y equals, enter, and now I get that nice fraction bar. The top part of the fraction was negative 5, and the bottom part of the fraction was 5 times the square root of 5. Not grabbing some reason. There we go. You don't have to close the parentheses at the end. You can if you want. I get 116.6 degrees. Now, if you don't have that very special fraction key, you're going to have to do inverse cosine of negative 5 divided by, and when you do this slash, you have to put parentheses around the whole denominator. 5 times radical 5. You see I get the same results. You got to make sure, if you're not going to use that special fraction key, you have to put parentheses around the denominator. I get 116.6 degrees. Okay? That's problem number 1. I'm going to pause it now. I'm going to do the other two problems and come back and show you how you did them. Okay, for this example, I did my magnitude of v and w. V is the same vector as before. Magnitude is 5. W I figured out to be 8 squared plus 6 squared square root of. The magnitude is 10. I did its dot product. V dot w turns out to be 50. And then I did my theta is inverse cosine of 50 divided by 5 times 10. Well, 50 divided by 5 times 10 is just 1. So inverse cosine of 1 is 0 degrees. That means that these two vectors are in the same direction. Okay, I'm going to pause it and do the last example. In this last example, everything was in i's and j's, so 4i plus 3j is really just 4 comma 3, and negative 2i minus 1.5j is negative 2 comma negative 1.5. I figured out their magnitudes. I did their dot products. I did theta is inverse cosine of negative 12.5 over 5 times 2.5. I got 180 degrees. These are going in opposite direction. These two vectors are going in opposite direction. Okay, again, all my notes are posted on the portal, so you can copy through there as well as I'm going through here. I'm going to go to the last page. On this last page, I'm going to have a couple examples on how I figure out the component form of many vectors. This is what we're going to be doing a lot of, working with what I call maybe word problems or real-life applications. Of course, you got to keep your calculator in degree mode, and we're going to round to 1 decimal. Okay? So I have two vectors here, A and B. Vector A, vector B, and I want to find the component forms. Well, just using those magic formulas of what we said before, vector A is equal to 30 cosine of 25 degrees, 30 sine of 25 degrees. I'm just going to put that in the calculator, and I'm going to round to 1 decimal. I'm not going to show that on the calculator. You could do that by yourself. And I get vector A is equal to 27.2, comma 12.7. And I get 2 positive x and y's, and it better be because vector A is in quadrant 1. Now for vector B, well, vector B is equal to 50 cosine of negative 70 degrees and 50 sine of negative 70 degrees. Okay, I put that in the calculator and I get vector B is equal to 17.1, comma, negative 47.0, and I better get that as a positive x, negative y, because vector B is in quadrant 4. Now, what if I wanted to figure out what is the net result? I'm going to do this basic for a second, and the result, vector R, is just A plus B. So I wanted to, I could do 27.2, comma 12.7 plus 17.1, comma negative 47.0, and my result is equal to 44.3, comma negative 34.3. That would be the net result of these two forces pulling on this block. Okay, now for airplane and wind. Well, for the airplane, 500 cosine 20, 500 sine 20. I get for the airplane 469.8, comma 171.0, and for the wind, I get 40 cosine, negative 42 degrees, and 40 sine of negative 42 degrees. And for the wind, I get 29.7, comma negative 26.8. Okay, if I want to see the net results, and I did this on my handwritten notes that you can look up on the portal, I add the airplane and wind components together to find the net results. That's what we're trying to do in the big picture. Okay, a couple more examples that we want to work on. They're not too bad. The first one, they want you to find the exact value. You're going to have to be given a special angle like 30 degrees. I'm doing this because some of the IXL assignments are like this. So my force vector will be 15 cosine 30, which is a special value. 15 sine 30 is another special value. And I get 15 times, well, cosine of 30 degrees is radical 3 over 2. And then 15 times sine of 30 degrees is 1/2. And I get as my final result, F equals 15 radical 3 over 2, and then 15 over 2. You're going to have examples like this on IXL that you have to type in things like this. 15 radical 3 over 2, comma 15 over 2. The next one, I just want you to go to thousandths, 3 decimal places. So vector v is 35 cosine 230, 35 sine 230, and when I'm done, I get it equal to negative 22.498, comma, negative 26.812. Again, you should realize at the end that negative x, negative y is in quadrant 3, and 230 degrees is in quadrant 3. Again, all my notes are posted, and you can follow along with them as long as watching this video. Thank you.